gave their alpha model, and it gives to the another atomic model, and in 1922 Bohr gave Bohr model. So if we start the Dalton model, so we can see that all the elements are composed of atoms, and they're indestructible like the solid sphere, and they cannot be created or destroyed, law of conservation of matter. And atoms of the same element are exactly alike, atoms of different elements are different, and compounds are formed by the joining of atoms of two or more elements. And so when we see the Thomson model, in 1897, J.J. Thomson actually discovered the electron, and William Thomson proposed that atom consists of small negative electron embedded in a massive positive sphere, and they call this model as a palm pudding model, and the electron were like current in a palm pudding. And in Rutherford model, so in 1908, so the English physicist Ernest Rutherford was hard at work on an experiment that seemed to have little to unraveling the mysteries of the atomic structure. And he discovered that there is a positive charged things inside the atom, and he called that things as a nucleus. So Rutherford reasoned that all of the atoms positively charged particles were contained in nucleus, and the negatively charged particles were scattered outside the nucleus around the atoms. In 1913, Danish scientist Niels Bohr proposed an improvement, and in his model, he replaced each electron in a specific energy level. So he proposed orbital. So a countable number of stationary states exists electron in a selection of allowed orbit radii, and electron radiation emitted when electron jumps or transition between these states, and classical rules apply to stationary state but not during transition between states. So this is the history of nuclear physics. So it started after the discovery of radioactivity by Henry Becquerel in 1896. And I have divided according to year and experiment theory. So in 1911, Rutherford discovered the atomic nucleus. In 1913, Thomson nuclear and mass isotope. And in 1932, Chadwick discovered the neutron. And at the same year, Heisenberg introduced about the isospin. In 1934, deuteron binding energy and explain of proton-proton scattering. In 1935, there is another revolution of theory, UFO model, meson exchange model, and from 1936 to 1951, there was development in experimental and theory as well. So alpha cluster Wheeler in 1937, fission Horn in 1938, liquid drop model, Bohr in 1939. And establishment of one pion exchange model, shell model, Wigner and Goppert, Mayer, Hansen, 1949. So in 1961, discovery of rho omega meson, vector boson, and the time between 1975 to 2000, there was a development. We can get two types. So one is baryon, another is meson. So baryon are very common, neutron and proton, the two common baryon, and meson, pi meson, and other meson. So when two quarks come together, it form meson, but when three quarks come together, they form a baryon. So if you see this figure, I think it will be more clear. So the example of field particle are WZ boson, photon, graviton gluons, and meson, pion pions, and baryon, common one, neutron proton, and other. So if we add these two as a group, so this particle are known as fermions, and because this particle obey the Fermi data statistics, and these are the particle known as boson. This boson named after the famous Bengali scientist Satyendranath Basu, and this particle satisfy the Bose-Einstein statistics. And if we break this hadron, that means meson and baryon, we get quarks. Quarks are the fundamental building blocks of matter, and we get six flavor. So up, down, trans, train, and top, bottom. So they make question arise: why do we study nuclear physics? So nuclear physics is fundamental physics for understanding our lives and the physical world around us, and it will give you the answer of many questions, like what is the origin of the universe, and what is the origin of nuclei like hydrogen, helium, lithium, iron, uranium, thorium, and whatever elements we are getting in our earth. So stars, how it form, and inside star how elements are forming. That means we can understand the stellar nucleosynthesis, and we can understand about how the heavy elements are formed after the supernova. Then it will give the idea about the Big Bang, the creation of chemical element of energy in stars, and on Earth nuclear astrophysics. So we know that all the in the universe are synthesized after the Big Bang. So there are three types of nucleosynthesis. So primordial or Big Bang nucleosynthesis, the nucleus which formed immediately after the Big Bang. Nucleosynthesis, the nucleus which are formed here. You can see the if we consider the start of our universe from Big Bang. So after Big Bang, we get three stable nucleus that is are formed, and that is known as primordial nucleosynthesis. So we know the stars are from the cloud, and those cloud includes the hydrogen and helium. So when this gravity actually attacks those cloud elements and form heavier object, and when the object mass, if we compare the mass with our sun, so if we consider our sun mass as a one solar mass, and it is 1.998 to the power 30 kg, so it is known as the solar mass. So if we compare with our sun, so the star and the object which can start burn, the minimum mass should be 0.08 solar mass. That means the about 8% of our solar mass. If the object contain the mass 8% of our sun, that object can start burning, and we can call that as a star. Otherwise, that shouldn't be a star. So then the burning is started, and we can find the evolution of star, their starting and their life cycle. And as we know, so star has a formation and there is a end point of star. So you can see the date of the star. It could be a black hole, neutron star, white dwarf, or supernova explosion. So inside this star, so using that burning process, we can get element up to iron 56. So later, when we see the binding energy per neutron curve, we can explain. I can explain you the why the heavier element can't produce by burning process. So, and this is the iron 26. So the elements heavier than iron are produced after the supernova, and there is a lot of process: RP process, P process, R process, S process. This is proton capture, this is a neutron capture rapid one, and this is neutron capture slow one. And as we know the periodic table and where the elements are made, we see. So these two elements are from Big Bang, and you can see this is cosmic rays. In primordial nucleosynthesis, we can gauge the stable one is hydrogen, helium, and lithium, but these are not stable. But we can gauge in cosmic rays, and there is you can get the element in small star. You can see carbon, nitrogen, oxygen, and up to in last star it gives up to iron by the fusion. But the heavier element, most of them are formed after the supernova. So then if we see the matter composition of our universe, we can get the almost 96% still unknown to us. Just we can explain 4%, and the 96% are dark matter and dark energy, and inside 4% mostly are free hydrogen and helium, and very few percentage is star, just 0.%, neutrinos are 0.3%, and heavy element are very less, 0.03%. You can see almost 24% helium, 73.9% are hydrogen, and carbon very less, oxygen also 1%, and other just 0.6%. And inside our human body, if we consider the where do we come from, and sometimes scientists treat us as a stardust. So the element inside our body should be come from any star. So inside our body, we have a oxygen about 61%, carbon 23%, hydrogen 10%, nitrogen 2.6%, calcium 1.1%, and phosphorus 1.1%. Other is just 0.9%. So we can understand that this element cannot be formed after the Big Bang. So just this hydrogen can be come from that, but most of the element should form inside the star. So when scientists call us as a stardust, it's very true. So we can understand the neutrons, proton, deuteron, and the nuclear structure by studying the nuclear physics and the decay, their decay, like alpha, beta, and gamma, and other reaction also. So nuclear processes are used all around us, and their key application in many aspects of our lives. So recently, the scientists are trying to establish a fusion reactor, and we have already using a fusion reactor for several decades successfully. So, and also radioactivity in medicine, industry, and research. So in cancer, security, and fundamental studies such as neutrino properties, double beta decay, and so on. So if we start from the nuclear properties, so this is the notation of any nucleus whose mass number is A and atomic number is Z. So if we consider this is aluminum, uh, mass number is 27 and it contains uh, uh, 13 proton and 14 neutrons. So all nuclei are composed of proton and neutrons. So exception is just hydrogen. Just hydrogen has just one proton inside that hydrogen nucleus. Charge, the electron has a single negative charge and it's 1.6 into 10 to the power minus 19 coulomb, and proton has a single positive charge and neutron charge 0. And we can understand that how the neutron become charge neutral and proton become charge positive. So if we go the quark model of proton and neutron, we can see proton can be formed by 2 up and 1 down. So if we these are the value of charge of up and down. If we put the value of up and down here, 2 up, that means 2 by 3 plus 2 by 3 minus 1 by 3, we can get plus 1. And if we put the value here, so 1 up, that means 2 by 3 plus minus 1 by 3 minus, you can see this becomes 0. So I think you can understand how this neutron become neutral and proton become positive. So then another interesting thing is nuclear force. So as we know, proton is positive charge and neutron is charge neutral. So how they form a how they bind together and form a nucleus. So they do this by using a very strong nuclear force called strong nuclear force, and by exchanging pi meson. And there is a similar force inside the atom, but this is not a nuclear force, this is a Coulomb force. So the force between a proton and electron, and the binding energy of deuteron. So the small nucleus whose contain 1 proton and 1 neutron is deuteron nucleus, and the binding energy of deuteron is 2.2 MeV. That means size of a nucleus. So we can see R equal to R naught equal to 1 by 3, where R naught is a constant 1.2 10 to the minus 15 meter, and we can get the density from this equation. And there are very large repulsive electrostatic force between the proton. So this force should cause the nucleus to fly apart. The nuclei are stable because the presence of another short range force, that means nuclear force. And this nuclear force is attractive force, and that act between all nuclear particles. And the nuclear attractive force is stronger than the Coulomb repulsive force at short range within the nucleus. Sorry. So if we see this figure, this is a stability curve. So this is the proton number in x-axis and y-axis. As the neutron number is increasing, the stability become decreasing. So it's become more unstable. So the most stable nucleus is calcium 40, and you can see after calcium 40, so the line should be go this way, and this is the more stable should be. But as the neutron become more in comparison to proton, so the line should go this way, and it becomes unstable comparative to this region. And so when we go the Z number greater than 82, so we can see it automatically decay in alpha decay. So this is the binding energy neutron curve, which I want to explain, and by this way we can explain the fission and fusion. So you can see this is the region of greatest stability. So every nucleus want to gain this region and want to come here. So the element contain this region, and they have binding energy per nucleon, the number less than this is about 8.7 maximum. So they want to go there. So how they can go? They can add together, fuse together, and to go there. So this region, they actually can do fusion reaction. On the other hand, if you go this region, is also if they fuse and their so they should go this region. So how there? So if they broke down pieces, they can go there. Okay. If we hit here by neutron, so they break into pieces, and those elements, those binding as so binding as neutron should be here.
Pritam,
Okay.
I have a question. So if I go to relatively lower mass number,
Here.
lower than 50, let's say, so we see for higher mass number there is automatic alpha decay, spontaneous alpha decays,
Yes.
kind of
Yes.
decays, right? As well as beta and gamma decays are there. So, but for lower than 50, let's say 30 or 35 or something like that, there we don't see a spontaneous alpha or beta decay.
Okay. So
what is the reason for that?
okay. So the region for alpha decay is that for this region, that means the region about more than 70, the Z number. That so the nuclear force can work very short range. So when the when the Z number is increased, so size is also increased. So there should be extra force. That means repulsive force of neutron due to the Coulomb diffraction already started, and so the region here, the Coulomb repulsion should be higher than this region. So that's why you can see continuous alpha decay than this region. And the region for beta decay is the nucleus should have one proton or one neutron extra. So if that nucleus contain one proton or one neutron extra, that nucleus could go by beta decay in any form. They have three types. Either it could be electron capture or electron emission or positive emission. So I think this could, so the Coulomb repulsion is higher this region than this region.
Okay, I understand. So basically, you are saying that N by Z graph that you have shown.
Yeah, from this we can
the
explain
stability
the
graph.
fission. Now from here we can explain the fission and fusion reaction. So, and from here, when I explain, I'll explain the about the fusion inside the star. Then you can see if we see that inside the star, the maximum fusion can happen silicon burning. There is no iron burning. So why iron cannot be burned inside the star. So if you want to explain that things, you have to come here also. So you can see this is the iron region, maybe this one, iron 56, this one. So this is the maximum one. So when iron fuse, what will happen? So two iron means 26, means about 52 number of jet nucleus. So 52 number of jet should become here. So this region is less stable than this. So no element, because everybody want to stay in a stable region, or want to be a maximum stability. So nobody go unstable region by nature. So but due to that, if we go inside the burning in star, we can see that there is no burning in star after silicon burning. Means there is no uh, iron burning is happening. I think we have a one slide later about it. I think we can explain it later also. So this is the very basic things of radioactivity. So from nucleus we have three types of decay. One is alpha decay, another is beta, and another is gamma decay. So you can see. This is the example of alpha decay, and when a nucleus decay alpha, so that nucleus actually become two lesser Z number and four lesser mass number, and the region is that I told previously. So that in this region they become uh, when the neutron number is increasing, so the dominant force of Coulomb force should be higher than nuclear force. So they become less stable, and that's why they want to break into small parts. And we know that why they become as a alpha, not as a one proton and deuteron. So there is another decay, this beta decay. So in the three way you can explain beta decay. So one is positron emission, this is positron emission, and this is electron emission, and this is electron capture. So here, so when neutron number is larger, so then this neutron become proton, and electron will emit. And to conserve electron number, there is electron antineutrino should be added here. And if we see positron emission, so the proton should become neutron, and positron it goes a huge chain reaction. So there is another reaction, fusion, that is actually happening inside star. So when two small nuclei come together and form a heavier nucleus by fusing both. So these are the when deuteron and tritium come together and they form a helium-4. So this is again the same binding energy per nucleon curve. I think this will give a more clear idea about the fission and fusion. So this red zone indicating this one are the region of fusion, and this after the iron 56 the region which go through the fission reaction. So the nuclear reaction, as I have already told that the mainly inside star, the main reaction is fusion reaction. The two famous reaction are happening in star. One is the PP chain reaction, another is CNO cycle, carbon nitrogen oxygen cycle. So you can see in a PP chain reaction, so when two proton come together and form deuteron, and when deuteron and another proton, it becomes 3 helium, and similarly here also 3 helium. When both 3 helium come together and it becomes 4 helium, and again we can get this hydrogen. So this is the chain reaction PP, and another is CNO cycle from carbon. When carbon 12 interact with hydrogen, so it becomes 13 nitrogen, and 13 nitrogen from 13 nitrogen by positron emission beta decay, we can get 13 carbon, and when 13 carbon interact with hydrogen, it becomes 14 nitrogen, and when 14 nitrogen interact with hydrogen, it form 15 oxygen, and they emit gamma ray, and it's unstable, and it will go 15 nitrogen by decaying positron, and again when it interacts with the hydrogen, so it becomes 12 carbon. So as it is started from here, so this is known as CNO cycle. So this is the picture of stellar evolutions from stellar cloud, how this due to the gravity, how the small star or heavy stars are formed, and during their life cycle they form red giant or super red giant, and when they end their life, they could be gone through planet nebula or supernova, and at the end they could become a white dwarf, brown dwarf, neutron star, or black hole, or other after the supernova, when the explosion, they can form another star or other things. So this is the life cycle of a sun. So it started from interstellar cloud by gravity, so it becomes firstly photostar, and then where we are seeing sun now, so it's become a star actively. This is like a youth time, so it will become red giant, so and at the end it will become a white dwarf. So then we can come in the application of nuclear physics and the modern technology of nuclear physics. So nuclear technology is the technology that involves the reaction of atomic nuclei, which has found application from small detector to nuclear reactors, and from gun sight to nuclear weapons. So nuclear energy has inhabited two distinct environments since in inception. One is the environment of nuclear radiation and their electricity. So as both the weapons and nuclear power rely on fusion energy, uranium or plutonium, and both are harmful for human being or environment. So we have to very careful about using this. So we need a proper technology of using this. So application of nuclear technology outside the civil electricity production in power plant are less well known. So we can also use this as in medicine, in agriculture, in industry, in scientific research, transport, and other also. Almost all form of primary energy come from nuclear reaction. If we consider that all the existing thing of Earth come from after the supernova from the star, so we can consider that all the energy comes from star or nuclear reaction. Fossil fuel and biofuel got the energy from sunlight. Geothermal energy comes from the radioactive decay or thermal energy left over from when Earth originally formed, which came from a catalyst, which make a nuclear explosion or supernova. Of course, nuclear ultimately get their energy from nuclear. This nuclear energy is potential energy stored inside the nucleus of an atom. The proton and neutron inside the nucleus are held together by strong nuclear force, which balance the repulsion of Coulomb force between the protons. The weak force balances the number of neutron and protons. Nuclear energy is released through three processes: nuclear fission, nuclear fusion, and radioactive decay. The Earth has limited supply of fossil fuel. So we are modern days we are using mostly coal, oil to uh, for our power supply or transportation, but it will finish very soon, maybe. So scientists are looking for another or alternative uh, source of energy. So later I can talk about the how nuclear energy could be the best alternative uh, energy source than other. So nuclear power plants could still produce electricity after coal and oil become scarce. A nuclear power plant needs less fuel than one which burn fossil fuel. 1 ton of, if you compare fossil fuel with nuclear power plant, you can see 1 ton of uranium produce more energy than produced by several million ton of coal or several million barrel of oil. And the extra plus point of using uranium is that uranium, nuclear power plant shouldn't emit any greenhouse gases or any harmful gases in the environment. But on the other hand, coal or oil, the power plant emit lots of actually the greenhouse gases. So this helps get rid of most of the carbon dioxide emission caused by the combustion of fossil fuel, thereby reducing the greenhouse effect. And nuclear power costs about the same as coal, so it's not expensive to make and is reliable. The application, so electric power generation, medicine, scientific research, food and agriculture, consumer product, industry, transport, space, water resources, and environment smoke detector. So agriculture. So the Food and Agriculture Organization of United Nations actually estimate that about 795 million people, 1 in 9, were suffering from chronic undernourishment in 2014-2016, these 2 years. So radioisotope and radiation used in food and agriculture are helping to reduce this figure, and as well as directly improving the food production. So agriculture needs to be sustainable over the longer term. The FAO works with the IAEA on program to improve food sustainability, assisted by nuclear and related biotechnologies. And fertilizer are expensive and if not properly used can damage the environment. So it is important as much as use fertilizer as possible is fixed in the plant matter, and that a minimum is lost to the environment. So labeling fertilizer with a particular isotope, for example, nitrogen 15, provides a means of ascertaining how much has been taken up by the plant, allowing for better management of fertilizer use. So we can use radioisotope for fertilizer management system. And plant mutation breeding. Plant mutation breeding is the process of exposing the sets or cutting of a given plant to radiation such as gamma rays to cause mutation. So during period of rapid population growth, the use of nuclear techniques has enabled Bangladesh and large part of Asia in general to achieve food security and improve nutrition. And insect control, estimate of crop losses to insect vary, but are usually significant. Despite the widespread use of insecticides, losses are likely to be of order of 10% globally, and often notably higher in developing countries. So one approach to reduce insect depredation in agriculture is to use genetically modified crops so that much less needed. Another approach is to disable the insect. Radiation is used to control insect population via the sterile insect technique, SIT. SIT involves rearing large population of insects that are sterilized through radiation, gamma or X-ray, and introducing them into neural population. Also, consumer products. So the function of many common consumer products in dependent on the use of small amount of radioactive materials, smoke detector, watches and clothes, and non-stick materials, among others, all utilizes the natural properties of radioactive isotope in their design. So the common use of radioisotope today in our household smoke detector is armenium 241, and this is the decay product of plutonium 241, and we can get this in nuclear reactor. Food irradiation. So some 20 to 30% of food harvested is lost as a result of spoilage before it can be consumed. So this problem is particularly prevented in hot, humid countries. So food irradiation is a process of exposing foodstuffs to gamma rays to kill bacteria that can cause foodborne disease and to increase shelf life. In all parts of the world, there is a growing use of irradiation technology to preserve food. More than 60 countries worldwide have introduced regulation allowing the use of the irradiation for food products. So industrial tracer radioisotopes are used by manufacturers as tracers to monitor fluid flow and filtration, detect leak and gauge engine wear and corrosion of process equipment. It can also use as a inspection and instrumentation. So radioactive materials are used to inspect metal parts and the integrity of the wells across the range of industry. For example, a new oil or gas pipeline system are checked by placing the radioactive source inside the pipe and the flame outside the well. Carbon dating, analyzing the relative abundances of particular naturally occurring radioisotope is of vital importance of determining the age of the rocks and other material that are interest of geologists, anthropologists, hydrologists, and the archaeologists, among others. And desalination, potable water is short supply in many part of the world, so lack of it is said become a constraint of our development in some areas. So nuclear energy is already being used for desalination and has potential for much greater use. Nuclear process heat for industry. Also, nuclear energy is an excellent source of process heat for various industrial applications, including desalination, synthetic and unconventional oil production, while refining, biomass-based ethanol production, and in future hydrogen production. Peaceful nuclear exploration, the USA and Russia have investigated and trialed the use of nuclear explosion for civil engineering purposes, though only one significant construction resulted, a dam of Kazakhstan. Some 150 experiments spanned from 157 to 75 in US, and in 1965 and 89 in this period of time in USA. So space, we can also apply this nuclear radioisotope in space. So unmanned spacecraft rely on radioisotope thermoelectric generator RTGs for the power they need to space exploration. And RTGs use heat from plutonium to generate electricity. The craft use this electricity to run the computer that control their operation and collect the process the vast amount of data, including images that are sent back to Earth. A typical RTG produce about 30 watt of electricity and will operate unattended for many years. Nuclear medicine has application across a broad spectrum of disease, focusing particularly on oncology, cardiology, and nephrology, orthopedics, and nepropsychiatry, nuclear medicine therapies for lymphoma, bone, liver, and neuroendocrine, and so on. So nuclear medicine techniques is oncology can localize primary tumors, delineates excellent of disease, and monitor response of treatment. So nuclear medicine application is treating the various disorders with different techniques like myocardial perfusion imaging maps the blood flow to the heart, helps in detecting the heart disease and determine the most effective course of treatment. Bone scan can detect the spread of cancer 6 to 18 months earlier than X-ray. Kidney scans are much more sensitive than X-ray or ultrasound in fully evaluating kidney function. Imaging with radioactive technetium iodine can help diagnose bone infection at the earliest possible stage. Nuclear medicine diagnostic procedure involve very small amount of radioisotope. Nuclear medicine therapy is an effective and safe treatment for certain conditions. Nuclear medicine therapy is used to treat overactive thyroid gland or thyroid cancer. Nuclear medicine therapy allows for quick, safe, early, and more accurate medical diagnosis. So over 1100 radioisotopes are available for clinical use. They can be used as a single photon emission computed tomography, CT, positron emission tomography, and magnetic resonance imaging, MRI. In archaeology, investigators can now measure a large number of trace elements in many ancient specimens and then compare the result with the concentration of components having the same origin. Crime detection, the examination of gunshots by measuring trace amount of barium and antimony from the gun powder has proven to be 100 to 1,000 times more sensitive than looking for the residue itself. And scientists are also able to detect toxic elements in the hair by a neutron activation analysis. And also mining and oil. So geologists and petroleum engineers use radioactive sources routinely to search for oil and gases. A source and detector are inserted down the exploratory drill hole to examine the metal and different depths. So here you can see plutonium, beryllium, or armenium, beryllium are using this. So how the question may arise, how nuclear energy could be the best alternative as an energy source. So nuclear energy comes from the energy stored in the nucleus core of an atom. So this energy is released through the fission, splitting atoms, or fusion merging of atom to form a larger atom. The energy release can be used to generate electricity. And fossil fuel, which mainly include coal, oil, and natural gas, fill the majority of the energy needs around the globe. And generation of electricity is one of the predominant use of fossil fuel, but this resource is limited. So it will finish after certain time. So we need to we need to find the another or alternative energy source. So nuclear energy is cleaner while generating electricity, and nuclear fission provides energy without releasing greenhouse gases such as carbon dioxide. However, nuclear power plant generate radioactive waste, a critical factor when doing a fossil fuel to nuclear power pollution comparison. So you can compare the coal fire plant with the nuclear power plant. So you can see uh, in coal fire plant, if we use 3 million ton coal per year, so it will give about 7 ton carbon dioxide waste, along with 0.3 million ton solid waste per year. And on the other hand, if we use 27 ton in wind power, geothermal, solar cell, hydropower, wave power, tidal. So we can, if we see the wind power is used to rotate a turbine, which turn an electricity generator. And here the energy changes from kinetic to electrical. The advantage is these are renewable energy, no greenhouse gases, no acid rain, no radioactive waste. This is good, but there is disadvantage is unreliable because needs wind for wind power. Best used in place where they will often be degraded as unsightly. So that means we need a heavy airflow for that. So, and it could be danger for wildlife, and also noisy. And many turbines are needed to produce same energy of a small thermal power station. This is a geothermal energy. In some volcanic area, hot water and steam rise to the surface. This steam can be trapped and used to drive the turbines, and this is known as the geothermal energy. And here, a thermal energy converted to kinetic energy, and then kinetic energy to electrical energy. The good thing is this is a renewable energy, no greenhouse gases, no acid rain, no reactive waste, and short startup time. But disadvantage is very limited location and expensive to build. Solar heating, uh, heat energy from sun is focused onto the pipes containing water. The water boils, producing steam, and this steam is then used to drive the turbines, which is turned electrical generator. Here, thermal energy converted to electrical, is kinetic and kinetic to electrical. Advantage is renewable, no greenhouse gases, no acid rain, and no radioactive waste, but disadvantage sunshine needed, and so best in desert region, can only be used during the day. A large amount of land needed to produce the significant amount of energy. Solar cell, electricity produced directly from the sun's radiation. Here, light can be converted into electrical energy. So the advantage is renewable, no greenhouse gases, no acid rain, and no radioactive waste, instant startup time. But there's some disadvantages. Unreliable UK sunshine needed for solar cell can only be used during the day. Only the 10% of solar energy is converted into electricity. So we need to increase the efficiency. Many cell needed to produce the significant amount of energy. So in hydroelectric power also, there is a advantage, and the disadvantage is very limited location, wildlife affected, expensive to build up, and wave power also have some disadvantages. Unreliable, can only be used in areas with suitable waves, danger to shipping. Tidal power also some advantage, but there is some disadvantage also. So very limited location, wildlife affected, expensive to build. So if we see the power come from which energy source. So we can see the contribution of nuclear about 5%. So nuclear provides 5% total energy and 10% of global electricity generation. So if we in power they use 5% and global electricity generation they contribute about 10%. So here the other contribution of power comes from coal, natural gas, petroleum, biofuel, and solar, hydro. So if we see this figure, we can see the on the basis of century. So in the 15th century, we have just two energy source. One is from animal, another is the biomass. So as the time goes on, in the mid of 19th century, we have introduced a new energy source, coal. And in early 20th century, we have introduced oil in our energy source. And in late 20th century, we have introduced natural gas and nuclear. And in mid of 21st century, uh, we'll use hydrogen. So if we compare the general power plant with a nuclear power plant, we can see the thing is almost same. So here we can get heat by burning coal or oil or gas. So we get steam, and this steam turn the turbine, and it will uh, give the electricity by the generator. So the same thing happened. The heat uh, here in nuclear power plant, we can get heat from nuclear fission. So this one, but the rest of the thing are same. So this is a pressurized power reactor, the schematic diagram. So inside the nuclear reactor, there is a fuel, there is a coolant, moderator, materials, and control. So in fuel, there is a material, ceramic, metallic, particle, and dispersion nitride. And we can use uranium 235. And in some nuclear reactor CANDU type, we can use this 238. So in natural uranium, we can get almost 99.3% are 238, just 0.72% are 270, sorry, 235. So we have to increase the percentage. So we need enrichment. So enriched uranium is the uranium in which the isotope 230 has a concentration greater than the natural one. So here just 0.72%. So we have to increase this percentage up to 3 to 5%. So this is the same figure as I have already explained in earlier slide. So inside nuclear reactor, the basic nuclear reaction is this one. So when a thermal neutron come to 235 uranium, so first it will form a compound nucleus 236, and then it will break into two nucleus, and this is the chain reaction. So there is other where this nuclear experiment are happening in the other experimental lab like CERN and also in Fermilab. So in experiment and in nuclear power plant or wherever we are using nuclear energy, so we have to consider about the radiation safety and protection. So natural sources of radiation are present throughout the environment. So in general, natural radiation sources are difficult to control, and it is impossible the public to completely avoid being exposed to them. Radiation source have many beneficial applications also in medicine industry and research. So what is radiation? Radiation is the kind of energy which is emitted or transmitted from some source in the form of waves or particles through space or through material media. So some radiation are visible and detectable by human sense, such as sunlight, but some are invisible and need to suitable instrument to detect, like X-ray, gamma ray, or other. So types of radiation. So we have electromagnetic radiation, particle radiation, acoustic radiation, gravitational radiation, cosmics, and the radiation from sun and deep sea. So in electromagnetic, we have radio waves, microwave, visible light, X-ray and gamma ray, particle radiation, alpha, beta, neutron radiation, acoustic, ultrasound, normal sound, seismic wave, gravitational radiation that takes the form of gravitational waves or other ripples of the surface of the space. So we can impact on matter. So how it will impact when it interact with matter. So there is ionizing radiation and another is non-ionizing. So we have to care about this one. So this is non is the radiation that carries energy, enough energy to liberate electron from atom or molecule. So it is made of energetic subatomic particle like ions or particle ions or atom moving high speed. So the electromagnetic waves are on a high energy and of electromagnetic spectrum. So the example are electron, proton, alpha particle, heavy ion, indirectly ionizing radiation, X-ray, gamma ray, neutron, and non-ionizing radiation. Radiation is a type of electromagnetic radiation that does not carry enough energy to ionize atom or molecule. So these are visible light, infrared, microwave, radio waves. So in our daily life, we are go through a lot of uh, radiation, or we are living inside radiation. So we are taking radiation through food, through environment. So as I have already told that we don't care about this non-ionizing. So, but we have to care about the ionizing radiation. So, if we are working near or inside a lab where radioisotope or radioactivity are using or radiation are using, so we have to regularly check the radiation dose. So the other uh, uh, thing, so we in which source the we are getting the radiation. So you can see from medical, it gives almost but to almost 50%, almost 50%. That means 36, yeah, almost 50%, and uh, just few percent are come from occupational and industry, and background. And among background, radon and thoron gives 30%, and from space 5%, and internal 5%, terrestrial 3%, and consumer 2%. So if we compare the radiation dose per year, so we are staying near the nuclear power plant, and we are uh, doing a whole body CT scan or X-ray. If we compare, so if a person stay near the nuclear power plant, so he can get uh, dose about 0.01 millisievert per year. On the other hand, each uh, X-ray will give 6 millisievert, and one CT scan will give 10 millisievert. So that means uh, 1,000 times larger than staying near the nuclear power plant. And if we travel from Tokyo to New York, you can get almost 100 times larger radiation than staying near the nuclear power plant, and 6 times large less. Sorry, if we do a chest X-ray, you can get 6 times larger radiation than staying near the nuclear power plant. So to make a good shielding or environment uh, radiation free near the uh, nuclear power plant, we have to care about some radiation. So we have to care about alpha, beta, gamma, and neutron, because uh, this is the main reaction of nuclear power plant. So neutron interact with 235 uranium, and so if we see the all the possible reaction, we can get this four type of radiation: alpha, beta, and gamma. So if we check that if I add a paper, we can block alpha. If I add a sheet of aluminum, we can block the beta. And if I add a lead sheet, we can add gamma. And if we add concrete, we can get, so we can block the neutron. So here, this is the safety system of nuclear power plant, and this will actually protect the all these radiation which are uh, come from nuclear power plant. So the conclusion, nuclear physics is an important pursuit because the study of the nucleus of the atom is at the heart of our ability to understand the universe. It provides the answer and expand our knowledge of both the infinitely small and extremely large. So this application includes the device and technologies for medical diagnostics and therapy, energy production, exploration, safety, and national security, and for the analysis of materials and environmental contaminant. Nuclear physics and its application fuel our economic vitality and make the world and our lives safe and healthier. So thanks for all of your patience. I think uh, I tried to uh, talk very simple things of nuclear physics and its application in our daily life. And if you have a question, I think you can ask.
Thank you, sir, for this wonderful presentation. Now I think we can move on to our Q&A session. So please, if you have any other questions, please ask, sir.
Hello.
Hi.
Hello, Pritam, very excellent talk and very detailed.
Thanks.
Really enjoyed it. I had a very naive question. What determines whether a nucleus will go through a alpha decay or beta decay, for example? What differentiates between that? I understand the stability curve of N versus Z and also the fusion versus fission curve. But from those two curves, how do you come to conclusion? Yeah.
Sir, I think you are muted, so we cannot hear you.
I think from that curve, you can explain the fission and fusion. But if you want to explain beta decay, so the first thing you have to understand that how beta will decay, how a nucleus will decay beta particle. So the nucleus who contain a extra neutron or proton. So that means we know the stable nucleus means almost same number of neutron and proton. If a nucleus, and that means the if isotope of a nucleus who have a larger neutron number or larger proton number than neutron number, or larger proton number than neutron number, or larger proton number than neutron number, then it will go beta decay. So by uh, forming that extra neutron into a proton. So when I have already showed that, so when a extra neutron become a proton, it will decay a electron, and to conserve the lepton number, so it will also decay electron antineutron. And on the other hand, if a nucleus have extra proton, so it will form that proton into neutron, and it will emit a positron, and to conserve electron number, it will also emit a electron neutron. So, but on the other hand, alpha decay. So, alpha decay actually mostly happen for the nucleus whose Z number is near about 80 or something like that. And I explained that. So, in that region, the Coulomb force is a bit larger than dominant than the, because as the radius of size of the nucleus is larger, so so the number of neutron also, if we see the stability curve, so after 40 calcium, the number of neutron become larger, so it will reduce the nuclear force than the Coulomb force. So the Coulomb force is dominant in that region, and uh, so they actually decay the alpha. I think this could be the region.
Okay. So you mean the heavier nucleus are mostly dominated by alpha decay, and
Yes.
the less heavier are for beta decay. Basically, the isotopes which are radioactive. Okay,
Yes.
fine.
Well, if anyone else have any other question, please feel free to ask, sir. So someone have asked a question: how do they calculate the percentage of dark matter and dark energy if it is yet to be discovered?
Uh, Actually, uh, what the question is, how do you calculate? Okay, so I don't know the exact method. So, but we can calculate uh, through uh, the, the element composition, and I don't know the details. So, but the scientists are trying to find those dark matter or dark energy problem, and they're trying to solve those problems. So they roughly say that it's about 96%.
Can I contribute?
Yeah, of course,
Gamda? Yeah. So one of the ways this is calculated is from the equations of state of these matters, which are called Friedman equations. So we knows what are the constituents of these in some earlier times, and depending on the lambda CDM model, we can calculate what should be the percentage at different epochs. For example, in future, at present, at different times, what should be the percentage of these different elements. We can see that currently the matter contribution, the dark matter contribution is like 1/4, and the three-fourth contribution is the dark energy. But this is not the same for all epochs. In the earlier part, it was mostly matter dominated universe, and then radiation dominated universe, and now it is dark energy dominated universe. So depending on the what is the A factor, the scale factor behaves. Using the standard lambda CDM, we can calculate these constituents percentage at different epochs. Yeah.
Thank you.
So someone in the chat have asked, are primordial black holes, do primordial black hole exists, or it is just a hypothesis?
Okay, so uh, are the primordial black hole exist or just hypothesis? So actually, I'm not sure about it. So we have the theory about the primordial black holes. So I think if anybody can contribute about this question, I think it will be better.
May I, Pritam?
Yeah, of course.
Yeah. So there are some attempt to understand different composition of the galaxies and to understand whether the primordial black holes can be incorporated into that. But there is no direct evidential proof till now that primordial black holes do exist. Recently, there is a attempt to understand whether the primordial black holes can contribute to gravitational wave, but we have no conclusive proof till now that it exists actually. So till now, it's a hypothesis.
Okay, there is another question. Excellent. Sorry, whether nuclear energy is safe or not. So I have already explained that. Okay, so if you uh, if you use with proper uh, safety system, that means we have to uh, use the nuclear energy with proper technology. With the proper technology, that means that should have latest technology, should have uh, uh, the latest technology to block the radiation, because the radiation is the main issue in nuclear energy. So if we control the radiation, this is safer, and it is the best in comparison to other. I have already compared with the other renewable one, so they have some limitation. But the bad thing is that we have to care about the radioactive waste and the radiation safety. And if we can control these two, then it is safer. It is good than other.
Thank you, sir, for this wonderful presentation. I think with that, we can end our session for today here. So first of all, thank you, sir, for teaching us about nuclear physics and giving us this showing us this wonderful presentation and making us know what nuclear physics is and what can it be in future. And also, thank you to our collaborator, SS Citizen Science Group, which is a WhatsApp group which promotes citizen science projects among students and teachers and colleges and schools. And also, lastly, thank you to all our participants for participating and making this session a successful one and encouraging us to proceed with wonderful sessions like this. Also, I provided a feedback link in the chat, so please follow that link. And also, our website link is also provided in the chat, so you can also visit there for more of our contents. And also, we will be streaming this. We have streamed this session on YouTube, so if anyone wants to see the full video of that this session, you can also see that full video. Thank you, everyone, and have a nice day.
Thank you. Good night.